So last time, if you can call it an issue, we call just x and y over here at the A0, and I said I wanted to look at inputs and outputs just to get the feeling from where things come from, and name the lines we see. And we had a line here which is just called y, because we don't know why. So it goes through all the address pins which are up here, but it also goes down here. So we look at that, and the other thing is the address generator registers over here, or memory pointers actually. So let's have a look at this A0 thing. So see, there you have the tuba thing, right? So I have drawn a little symbol here to show you what this big transistor actually does. So you can see it's two transistors. One of them is on at once, so but none of them are on if y is 0. So that's interesting. So it's basically disabled when y is 0. And if you like to follow how I found this, you can actually look at this. The signal comes in here, which drive the output pin, and when a line crosses here, it forms a transistor. And since this net here is connected to, it's connected to ground over here, that means that when this one is on, it can pull this one down. This is a pull-up to 5 volts, so we know this is a inversion. So therefore we write x inverted. So then we know we have x inverted here. And now it becomes a bit more trickier. X and y must be on at the same time for this net here to go to ground. So x naught, which is the gate here, must be high, and y must be high for it to go low. Therefore you have the bar over there. Right, so then you have that expression. Take that expression up here, and then we see this is simply just another inverter, so we just remove the bar we have here, and I've called it A0 up and A0 down, so basically. So you can also see that this inverter or X, it goes through two places, and when you do that you get x naught here and you get x there. So what you end up with is this thing here though, which is basically, we can call this a decoder, 1 to 2 decoder actually. That's interesting. So this output pin is disabled when y is 0, and we can follow it. I have an orange line here, you can see it's here also. Maybe you should turn on this to see. Yeah, okay, that was A11. And we found something interesting. I found so many strange things that I have to look at later, but like, why have they done this? It's like, kind of looks like it's possible to program it later or for experimentation, maybe. Sorry. This is the clock input. It goes to a big clock network. This is the color clock. It's not too interesting right now. Then we get down here. So you can see these are the driver for that line. So what I did then was to try to trace what is driving these guys then. And that's what I did in the clock generator thing. So anyway, we found phi0. The B here is just, it's the buffer, the large buffer. Can look at that. So it's a clock. Okay, so that's interesting. I don't know what set is right now, so that we'll have to find another time. But remember phi0. Go back here. This is the timing diagram for a raster line. So basically one line on the screen. This is during a bad line, so every 8th line is a bad line. So bad line just means that the CPU doesn't have access for a longer period of time, and the reason for that is the VIC needs to collect characters for the next line. So it needs more data than usual. You can see down here it doesn't need that data here. But what's interesting though is that when the VIC has the bus, the ASC is 0. This is a signal for the system to enable access, and you see that phi0 is 0. So it's closely related to phi0, and that's why we have phi0 here. So. And then, if we move out, what do we have actually? So, if we can follow this line, look, it goes down to phi0. Sorry for this overlay thing. It's really cool, and then you have AAC there. So, and these two are very, very closely related. You can see here that maybe I should turn this one on again. No. You can see that they are actually driven by the same line. However, we saw in the diagram they are very close, but there's something holding it low for a longer period of time here. So so we have this enable pin, and the main reason for that is basically that the CPU, when the CPU has the bus, then we don't want to drive the address bus, right? Because then the CPU is driving it. So that's it. Hi guys. So this is the next day, and I wanted to talk a little bit about the clock circuit. And I will just refer to an older video because I have talked about it before. But these are the clock buffers. They are very central to everything. The thing is that this is an 8565 chip. On a C64 VICII, you don't have 12 volt in on the VIC. So how do they get such a strong pull-up then, if they only have 5 volt to go by? Because if you want to drag a transistor or the output of the drain, you need more than 5 volt to turn it on hard and fast. So you can see this capacitor is interesting. It's not shorted together anywhere. These two layers, you have a red layer and then a green layer underneath. This is a capacitor in dieshots. And if you look at my video, the bias generator in question, I have drawn this circuit here. So this is the output buffer, right? So here's the output, and here are the inputs. And there's a lot of things going on here. And I think that is to get a symmetric switching, and because you have non-overlapping clocks. So what happens is that this capacitor is charged up. So when it's on, this network here is on. My hand is in the way anyway, but that means that this one's on. So this one is pulled up to 5 volt, and here it's pulled down to ground. So therefore this is charged. Now when the situation changes, this goes off. This one goes off. But there's still 5 volt here, but this one turns on and drags this one up to 5 volt. But what happens here then? If this side is now 5 volt or 4 volt maybe, well, then you have 5 volt plus 5 volt, so you have 10 volt, which again comes up here and then drives these guys. So you have more than 5 volt in there. So that's just something I wanted to mention. Yeah, so let's talk a bit about $18 read and write. So last time we said that we were going to look at these registers up here, which has to do with the memory pointers. So I've been doing that, and we saw down here that there was some decoding going on. You can go down there. These are all the address lines going across here, and here we found that there was number 18 is the memory pointer address, and then together with read and write strobes, which comes for the control line, they form a strobe for read and write for that register. So, and we follow them up to the register for CB11. And the reason why I know this is CB11 is one, it's $18, and we have data bus 1, so you can look in the register table and see that, okay, so if it's the bit number 1, then it's CB11. So, and I have drawn a diagram here to make it easier to explain, because when I say this one's 1 and this is 0, it's not always making so much sense. So, my very first videos I talked a lot about this, but this will be like a recap. So, so you have data bus 1 here, comes in here, and it's sort of gated either via read or via write on both sides of this too. In here you have a latch. You can see there's like a circle of information like this. So that when you have a latch, you have storage. Also, you can notice that this circuit has a sort of gate here. So, and this is from the buffered clock driver, ph0. The thing about that is this network is floating. It's not connected anywhere. So therefore it needs to be refreshed. So let's say it's been written one from the database is 1 here, you get 1 in here. That will only live for a short amount of time. So, but for every 1 microsecond you get ph0 high. So we get 1 here, turns this one on, this is ground, this goes to ground, this is connected here, this is 0, which is not connected to ground, so it pulls up to 1. So 1 is here, and then comes the clock, and then the 1 is fed out here again. So it sort of refreshes that 1 that already was there. So it sort of keeps itself latched. Maybe easier to show it on this side. I have actually made a mistake here. For read, I thought maybe it had to read it out here, but I see now it's directly from this driver here. So anyway, so if you look at this diagram, you can see here you have the capacitor, which indicates that this network is floating and has some parasitic capacitance. So it needs to be refreshed, and the way it's refreshed is via this transistor ph0, which you have over there. So you have the value CB11 and you want that out. Then you get a read pulse here, and the CB11 is then transferred out here, or driven, or it's driving DB1. In the diagram I have made a mistake here, so it pulls from this one, so it just discharges this one, so that wouldn't work. Actually this transistor is supposed to be up here, so yeah. So when you get a write, this one goes on, the value on DB1 is then passed into the latch, and then it latches on that value. So therefore you get CB11 here. So if you put CB11 on DB1, you get a write, it's put in here. Over here it's been CB11 not, and then it's inverted again to CB11, and so on. So it keeps itself latched. So basically that's it. It's not that interesting actually. What's interesting here maybe is what's going out of this register, where it's connected, what is it controlling? And that's something I try to figure out. You have a net here, which it's driving. You have some mysterious thing here, which I don't really know yet what is. It can also pull this network down. So you see, I have CB11 here, which drives a transistor here, which drives this big network, and you see a lot. This is a large pull-up. It's much larger than these guys here. So the way I see that is, if the channel is long and thin and narrow, there's not so much. There's a lot of resistance. If a channel is wide and short, then the electrons don't have to travel so long, or the current, and you have the width that makes it strong. So yeah, current has a linear relationships with the width and length. So anyway, I'm digressing here. So you can see it drives this network, and what I come to see that it's incredibly long. It's so damn long. Another thing you can see is that CB11 controls this network, and so does this thing on DB5. Now DB5 so there's 0, 1, 2, 3, 4 0, 1, 2, 3, 4, 5. So that's VM11. So that's video matrix 11. And basically that's address 11. So so this has to do with A11 also. Both of these have to do with A11. That's why they are connected together, I think. Not sure yet. You can see it has the same type of register. This is the latch, this is the output of the latch. Something enable thing going on here. There's a driver for this long network. This network keeps going and going, so let's try following it. See, where does it go? But this guy over here is the character counter. See that C up here? That's the character address counter. So I'm looking for the refresh counter. I'm not sure. So you can see it goes here. This is the video matrix. Over there it has 40 characters stored, and some color information in the last 4 bits. So you have 8 bits and then 4 bits for color. Anyway, it goes here. Let's go in there and see what that is. And it splits again. Look, there's a guy over there. And this is the character counter. So it's related. I have no idea why. But we did see this had something to do with CB11. So that's something at least. It doesn't go any further after that. So what does it actually drive? Don't know. Okay, I had misunderstanding. This counter is actually driving the same line. So for these networks we have many drivers. So there's a character there going back. It splits up here. Whoa. So this is like, oh, sorry, there. Oh, now it's getting interesting. This goes up there and then down again, right? Look, this is cool. It's A11. All of these guys are driving A11. Why didn't I think of that Oh, so silly, because CB11, that's A11, right? Yeah, so you have many drivers. So you have probably something will, probably this guy here will sort of, what should I say, turn, if this one is on, this, I called it enable to start with. This gate that controls this big network that goes to A11 will then be disabled, right? Because if this network is pulled to ground, this gate can not do nothing to that network. And the same goes for the VM11 here. We have another one, enable thing, but it's not the same enable. You can see they split. There you have another one. These are the same actually, don't know why. And I try to follow them. Let's see. Yeah, let's follow the white rabbit. So what is this guy? Don't remember if I figure out what it was, because time flies so fast. So it stops there. And we are also very close to the decoder for the timing, which is down here. There's another one down here for, I think this is for X, and this is for Y, or yeah, it's a Y. I remember this was a Y register, Y scroll, so this must be Y.